Hello, physics, and welcome back to Forces. In this video, I'm going to be going through problem 45 to show you how friction works. This is also another equilibrium problem, so this will kind of meld equilibrium and friction together and show you what happens when the system is in motion rather than when it is not. So when it is actually equal to MA rather than just being equal to 0. So I'm going to put some information up on the board, and then we will start. If you want to pull up or go into your textbook and look at problem 45 so that you know where we're starting from, we'll get going. All right. So if we read through this problem, it tells us that we're using this figure, which is on the previous page. This figure is on page 113, while the question is actually on page 114. So, objects with masses M1, which is 10 kilograms. So, M1 equals 10 kilograms. And M2 equals 5 kilograms. And it's actually 10.0 and 5.00. Are connected by a light string that is a string with no mass, so it does not contribute to our problem at all. A light string that passes over a frictionless pulley. Okay, a frictionless pulley means that this pulley has no friction, so as the string slides over the pulley is not inhibiting the movement of that string at all, which is really important. The problem gets a lot more complicated because if there is friction in this pulley, then the tensions are no longer equal, and so we have to solve for them separately. So yeah, we don't want that. That's pain. So frictionless pulley, tensions are the same. Frictionless pulley, as in the figure. When the system starts from rest, M2 falls 1 meter in 1.2 seconds. Determine the coefficient of friction between M1 and the table. So, falls 1.00 meters in 1.2. I forgot. Yes, 1.20 seconds. So, we know that this system starts at rest, and when it is released from rest, this falls 1 meter in 1.2 seconds. Using that information, we can start to solve this. So, the first thing we need to do here is we need to draw free body diagrams for each of the two objects, mass 1 and mass 2. Okay, including friction, because friction is present in this problem. Now, as a clarification, the hanging mass is not experiencing friction because it's not actually touching the side of the counter. And even though my diagram looks like M1 is hovering above the ground, it is touching the table, so it does have friction. So I'm going to draw a free body diagram for M1 and then M2. I'll do those down here, and then we will get started. So, first off, M1, we know that we have a tension force exerted to the side. So we have Ft coming this way. We have a weight force pulling down, Fg1. A normal force, because it is in contact with the table, there has to be a normal force going up, and because the problem is moving that way, there is a friction force exerted in the opposite direction. So there is a friction force this way. Okay? For M2, It is not in contact with anything except for the string, so there is no normal force and no friction. The only two forces that will be acting on a hanging mass are the tension that it's from its hanger and the weight of the actual mass. Now, technically, there is a buoyancy force on this, but the fluid that it's in is air, which makes that buoyancy force so small as to be irrelevant in this problem. And we're going to be ignoring buoyancy force in this whole chapter anyway, so I just wanted to mention it so you know we're ignoring it. So, two forces, tension up, weight down. Now, notice that I have specified Fg2 and Fg1 because Fg is the mass of the object times the acceleration of gravity. So, M1 is not the same as M2, which means that they're going to have different weights. So we have to specify which one's which. I did, however, use Ft for both tensions because the tension in the string is the same for both. Excuse me, or at least we are assuming it is because it's a frictionless pulley. And by the way, everything in this chapter, you're going to be able to assume that. Later on, at the end of the mechanics stuff, next semester sometime, I might give you a problem where you can't assume that, but that's like months away. So don't worry about that right now. Tension has to be the same. Acceleration of the system also has to be the same because it's a massless, stretchless string, which means that however fast this one is moving this way is also how fast this one is moving this way. So they have to experience the same velocity and the same acceleration, which is going to be really important here in a bit. So we need to write sum of forces equations for these. Now, I am going to take a shortcut on this rather than writing out all of the table and everything. I'm going to show you a shortcut version for this because all of our forces are in the x and y direction. There's nothing that actually needs split into components. So this is actually a lot easier than the vector addition problems that we've been doing in the past. So I'm going to pull my stool up so I can get up here and write this stuff out. So let's start by putting a separator and see if I can actually do a straight line this time. Nope. Oh well. So we need to do three sum of forces equations. 2 for mass 1 and 1 for mass 2. Okay, because there is no horizontal component of anything in this. It's moving exclusively up and down, or the vectors acting on it are exclusively up and down. So we don't care about the horizontal components of this one. We're going to start with this one, though, and because I habitually start with x, we're going to do the x force. The sum of forces in x first. So we have sum of forces in x for mass 1, the sum of forces in y for mass 1, and the sum of forces in y for mass 2. Okay, so for mass 1 in x, we have Ft and Ff. Ft is in the positive x direction. Ff is in the negative x direction. So we can write this as the force of tension minus the force of friction is equal to. Now, is it equal to? It's always equal to Ma. When it's in equilibrium, true equilibrium, and it's moving at either constant speed or not moving at all, we can say that A is 0. That is not the case here, though, because it is falling. This one is falling, which means this one has to be accelerating. Because of that, we cannot set this equal to 0 like we have in the past. So we're going to set this equal to Ma. Now, the A has to be the same for both masses. This mass has to be accelerating that way at the same acceleration as this mass is accelerating down. But they are not the same mass. So we have to specify M1. Okay? And its horizontal acceleration is going to be the same as mass 2's vertical acceleration. Now, can I get out of the way? Yes, I can. Okay. Now, if we look at y for mass 1, we have a normal force up, which is the positive y direction, and the weight or gravity force down, which is the negative y direction. So we can say then for y that the normal force minus the force of gravity of mass 1 is equal to m1a. But in this case, is this thing actually moving up or down? In case you were wondering or weren't sure, it's not. It's moving that way. Since it's moving that way on a horizontal surface, it has no vertical acceleration. So the vertical equation is still equal to 0. And that's a weird looking 0, but I'm going to roll with it. So the vertical equation is still equal to 0. Now, for mass 2, we have the tension up and the weight down. So we can say that the tension force, which is in the positive y direction, minus the gravitational force of mass 2, which is in the negative direction, is equal to m2a. But it's accelerating down. So it's negative a, which means it has to be negative m2a. This is an important distinction. You have to keep that in mind. Okay? Now, at this point, let's pause and take a step back. Okay? Because we have a couple of other equations that we know. Okay? We know that the force of gravity is defined for near the surface of the Earth to be the mass times the acceleration of gravity. And we know that the force of friction is defined to be the normal force times the coefficient of friction. So this allows us to do some substitutions here. So this first equation, we can replace Ff with Fn mu. Okay? So, I'm going to step down for a second. I apologize. Almost fell. So, with that in mind, we can say that the force of tension minus the normal force times mu is equal to m1a. That second equation we can turn into the normal force, and I'm going to go ahead and move this over, is equal to m1g, and that's pretty much it for that one. And then this third one, the tension force minus m2g is equal to negative m2a. Okay, so all I did there was I substituted in our definitions for FG and FF to get rid of FG and FF, to eliminate some unknown variables. Now, we do not know our tension force, but it's present in two equations, so we could set these two equal to each other. We also do not know our normal force, but again, it's present in two equations, so we could set those equal to each other. So I'm going to do that over here at the top and show you how that works. The real question is, where do I stand to do this so that I'm not actually in the way while I'm doing it? So there we go. That'll work. All right, let's start with this equation. Okay, we can substitute in m1g for Fn, right? Because Fn is equal to m1g. So we can substitute that in right here. We can also add m2g to the other side, and that will be equal to ft. In fact, I'm going to do that down here real quick. If I add m2g to both sides, then I get that ft is equal to m2g minus m2a. Does that make more sense? So you can see, and what I did there was, again, I did a little flipping on my negative signs. Instead of having negative 5 plus 3, I wrote 3 minus 5. Okay? So this is the same as this. So now up here, I can plug all of this together into one equation. And I'm going to start with this. So M1A, and I'm not actually in as good a spot as I thought I was. M1A is equal to let's start with the FT. So FT is M2G minus M2A. So M2G minus M2A minus M1G times mu. Okay, and I'm going to rewrite this a little bigger. I'm going to pause this and rewrite it a little bigger because that came out a lot smaller than I wanted it to. All right, so I've rewritten that a little bigger. Now I'm going to go get my blue marker again, and I'm going to re-underline some stuff that we don't know. Okay, we've eliminated FT and FN from this equation, but we still have two things that we don't know. We do not know A, which is present twice, and we do not know mu, which is present once. This is a problem. We have to know one of these in order to find the other. So this is where this information right here comes in. Okay, this is actually a kinematics equilibrium forces problem. We're going to use kinematics to determine our acceleration. And once we have our acceleration, we've already done the equilibrium portion. Once we have the acceleration, we can actually calculate mu. Wow, I missed that. Okay, we can actually calculate mu. So let's go to kinematics real quick and take a look at this. We know the vertical distance, or the vertical displacement. We know the time it took. Now, this is not a projectile, nor is it a free fall object, because it is not solely under the influence of gravity. Okay? There is a tension force resisting the fall of this object. And even if there was no friction at the top, there would still be a tension force resisting this. This will never be a projectile motion problem. Now, that is really important because it means we don't know the acceleration. That's why we're trying to find the acceleration. We cannot assume that the acceleration here is 9.8. Now, it cannot be more than 9.8. Okay? Can't be more than 9.8. 9.8 is the max. So if you do this calculation, you get an acceleration of more than 9.8, that can't be right. You need to go back and double check it. Okay? But we do know the initial velocity, and that gives us 3. It tells us in the problem, when the system starts from rest, m2 falls 1 meter in 1.2 seconds. We know that for these two pieces of information, VI was 0. So we have VI, we have T, and we have S. We're trying to find A. So which equation do we want to use? I would use the third one because VI is 0. So S equals bit plus at squared over 2. This is 0, so 2s over t squared equals a. 2 yeah. So 2 times our known s of 1.00, remember this 2 is an integer, divided by 1.2 squared, which would be 1.44. You can check me on that if you don't believe me. I'm actually going to check it just to make sure. I'm pretty sure that's right, because it'd be 12 squared, which is 144. Ugh. 12 squared is 144. We need 2 decimals. It might be 0.0144. Let's find out. 1.2 times 1.2. I'm right. Okay, cool. That's what I get for doubting myself. All right. So it is divided by 1.44 equals A equals 2 divided by 1.44 gives us an acceleration of 1.39 meters per second squared. Now we know everything except for mu. Now we know A, we know also A, which has to be the same. M1 and M2 were all provided in the question, and G is a constant. So we need to solve this equation for mu, and that's it. So first thing we want to do is we want to make this term positive first off, just to make our lives easier. So I'm going to move this to the other side and this back to this side, okay, which is going to give us M1G mu equals M2G minus M2A minus M1A. And then I'm going to divide both sides by M1G. So mu is equal to M2G. I'm standing in the way, aren't I? I hope I wasn't in the way from all of that. M2G minus M2A minus M1A divided by M1G. And at this point, we just plug in our numbers. So M2 was 5. So 5 times 9.81 minus 10 times the acceleration we just calculated, 1.39, minus 10 times, wait. 2 is 5. This should be 5. This is 10. Yeah, okay. Times 1.39 all over 10 times 9.8. Okay, I had to pause that for a bit of a sneezing fit. So this has to be equal to mu. We need to put an additional set of parentheses around the entire numerator to make sure that this gets done correctly. Okay, and I would also put each of these individual terms into a set of parentheses as well. So this gets its own set, this gets its own set, this gets its own set, and the denominator also gets its own set. So I'm going to plug this into my calculator now. Open, 5 times 9.81. And remember, this is 5.00, this is 10.0, so we have 3 digits in everything, so our answer should be 3 sig figs. Times 9.81, close. minus open 5 times 1.39 close minus open 10 times 1.39 close divided by open 10 times 9.81 close equals. Now, coefficient of friction cannot be more than 1. So if you get a coefficient of friction that is more than 1, it's wrong. Unless it's like Velcro or tape or something that's actually adhesive. Those have coefficients of friction like 5, 10, something like that. So, but you're not going to ever be working with that, so we don't need to worry about that. Your coefficient of friction should never be higher than 1. And this one comes out to 0.287461774. The 3 sig fig version of that number would be 0.287. Equals mu equals 0.287. Coefficient of friction is the ratio of the normal force and the force of friction. So it is a unitless value. Okay, so coefficient of friction has no units. So our answer should be 0.287. Now the fun part, I'm going to check in the back of the book and see if I did this one right before I end this video. So I will be back in just a second. I did. Yay! All right, so that's it for this video. That's friction, and that's another good look at equilibrium problems and another way to do them. The next video will be a tilted problem, where we actually have to do a rotated coordinate plane, and I'll show you exactly how that works. But that is it for this video, so have a wonderful night, and I will see you guys back in class.